Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, minimum sum of values by dividing array. The problem is actually a hard problem, and it is hard because it requires dynamic programming with binary search and some sort of bit manipulation as well. But as always, we'll start from the very brute force solution, and I will show you the step-by-step thought process that one should have while solving these kind of problems in general. So by the end of the video, I would hope that you not only understand this problem, but build a thought process that you can apply in similar problems during the contest. So with that, let's get started. The problem states that you are given two arrays nums and andValues of length n and m respectively. The value of an array is equals to the last element of that array. Now you have to divide the array nums into m disjoint contiguous subarrays such that the ith subarray bitwise and of the subarray is equals to andValues of I, right? So you have to divide the given array nums into m contiguous subarray where each subarray andValues is equals to the value given in the second array andValues. Your task is to return the minimum possible sum of values of m subarrays nums is divided into, right? So if it is not possible to divide the array, you have to return -1. So let's take an example. Let's say nums is 2357775 and andValues is 075. That is, you need to divide this array into three subarrays, three disjoint contiguous subarrays, such that the and of the first subarray is 0, and of the second subarray is 7, and of the third subarray is 5. And you have to do this in such a way that the value, a sum of value, is minimized. So there are three possible ways to divide this array into three disjoint contiguous subarrays. First one is 2, 3, 5, 7, 7, 7, and 5. You can see if you do and of 2, 3, and 5, you will get 0. So that matches here. If you do and of 7, 7, and 7, you will get 7. So that also is satisfied. If you do and of 5, you will get 5. That also is satisfied. Similarly, these two are also valid combinations. Now, what is the sum of values? Notice the value is equals to the last element of the array. So the value of 235 would simply be 5. Value of 777 would be 7, and the value of 5 would be 5. So sum of value is 5 plus 7 plus 5, 17. So this approach of dividing the array has a sum of value of 17. Similarly, this approach of dividing the array has a sum of value of 19, and the last one also has a sum of value of 19. Among all of these, you need to figure out the smallest one, and smallest one has a sum of 17, and hence 17 is the answer, right? So hope the problem statement is clear. Now, how to approach this? Let's assume this is the array you have, and this is the andValues you need to have, right? Now, you know the first subarray would start at 0, right? And you also know the first subarray would have a and value of 0. So let's see what all first subarray could be. So can this be the first subarray? Answer is no, because the and of all the element in this subarray is 3, which is not equals to 0. Can this be the second subarray? First subarray? The answer is no. And is 2, but and we want is 0. Can this be the first subarray? This time yes, because 3 and 2 and 5 is 0, which is matching the required and value. So this can be one possible first subarray, but it doesn't mean there are not others. There can, like, this is also another possible first subarray, right? Because the and value is 0. Similarly, this is another possible first subarray, and so on and so forth. So let's fix one. Let's say you fixed this as the first subarray. Like, we will try out all possible combinations, but for now we fixed the first subarray as this. Now what is remaining? Remaining is this array 7775 and these two divisions 7 and 5. So you need to divide the remaining array into two parts. The first part should have and value of 7, and second part should have and value of 5. and you need to do this such that the sum is minimum possible. So isn't this problem exactly equals to the original problem? Original problem was we have to divide this entire array into 3 subarrays. First one has a end of 0, second one has an end of 7, the third one has an end of 5, and we have to do this such that the sum is minimized. Now what is the smaller version of the problem? The smaller version of the problem that we are now looking at is, this is the remaining array, or this is the array divided into 2 subarray such that the and is 7 and 5 respectively, and do this such that the sum is minimized, right? So hope you can see the recursion here. So we have two things in our function. First is the first array A, let's call it, and second is the AND array, right? And what is the approach? Approach is, we will first figure out all possible versions of the first subarray, right? And for each of these possibilities, I will just simply have one more f function, with reduced array and reduced AND array, right? So let's try to formulate this for the index 0, right? So if you are starting at index 0, you have this array A, you have this array AND, right? Now you know that 3, 2 and 5 is something that must be there, right? So in this particular case, you can assume it as 2. So you know that up till 2 everything is there. So this is your first array, and if you take this as first array, what you need is, give me what is the minimum sum to divide the rest of the array into the required number of partitions. And once you get this rest of the, what is the sum for dividing the rest of the array, you can simply add it with the current value, which is the last element of the current subarray, to get what is the total value of this particular partition. That is, the first subarray is 3 to 5, and second and further is the minimum possible, right? Now you will now try the next partition, that is let's say 3 to 5, 7. So again you will see this is the first partition, so this value is 7. Now you want 2 more partitions from this remaining array, so you will simply call the same function. You will say, okay, what is the total minimum sum that I can have, in which I need to partition these array into 2 subarray with AND value of 7 and 5. Whatever is the minimum sum, you will add it to 7, and that will give you what is the total sum for this particular partition, where the first subarray is 3 to 5, 7. And you will simply keep on doing this for all possible combination of the first array or first subarray, and just take the minimum across all of them, and that will be your answer, right? So hope this entire thing is clear. Now we don't need to pass the entire array around. Why? Because we know that we are only dealing with suffixes. Why? Because let's say you tackle the first array, so you have removed the first subarray here. Now once you remove the first subarray, the remaining array would simply be a suffix of the original array itself, right? Because what we are doing always is just removing the first subarray. So if you remove first subarray, whatever is remained will be the suffix of the original array itself. So instead of copying the entire array around, you can simply pass in an index. This index will tell you what is the remaining suffix you need to partition, right? And in the same fashion, you can pass in an index for this AND value as well. So let's call it parts array, like different parts. So you just pass this, you pass I and P. I denotes what is the remaining array to partition, and P denotes what are the remaining parts we need to partition it into, right? So in the same fashion, you can have I plus 1, and this will be simply P itself. And finally, for this one as well, you will have I plus 2 and p, and this you can call it as 0 and 0, right? So this or rather p minus 1 you can make it. So this is how your recursive function would look like, and you will simply take minimum across all of them, and that will be your answer for f of 0 comma p minus 1, right? So let's look at the pseudocode. The pseudocode will exactly be similar to what we just saw. We have some base condition, we'll come to that, but what we are doing inside this is simple. We go over all possible ending of the first subarray. So we keep on trying out all possible ending from index to n, and whenever the AND value matches the AND value required for the current subarray, I will simply take the minimum across the current partition and all the previous partition that I had. So the current partition would be starting from index all the way up to next. So the value of the current partition would simply be array of next, because that's the last element of the subarray, and the remaining partition, the sum would be f of next plus 1 comma part plus 1, right? Now there are some base cases. Base cases are like if you have exhausted all the elements of the original array, then you better don't have any parts left. If you have some part left, then what does it, let's say you are here in the parts array, right, and you are here in the original array. So it means that from 0 elements you need to create one part with AND of 5. That is impossible, right? So that's where we return infinity, very large value, because we are taking minimum, so infinity would nullify that. And similarly, the second base case would be if we have exhausted all the parts, but we still are we still have to take few elements of the original array, then also it's not possible. For example, let's say you are at here and you are at here in the parts array. So what does it mean? This means that you don't need any more part, but you still have 2 more elements left. So that is also an impossible scenario, because whatever you have partitioned into is not correct, right? So in that case as well, we are returning infinity, right? So hope this this solution makes sense. The time complexity to this solution would simply be number of different states of this multiplied by what we are doing inside each of this state. Notice that we are all doing memorization already, so we don't need to worry about the exponential part. Rather, we will compute one state exactly once. So number of states multiplied by what we are doing inside each of the state. So inside each of the state we are doing order n operation, right? And how many states are there? Number of indexes, which will be n, number of parts, which would be m, right? So overall complexity is order n into nm, which is order n square m, right? This will not pass the given time constraint, because the value of n is 10 power 4, I think. Yeah, value of n is 10 power 4, so this will not pass the given time constraint, and we need to optimize this. Now if you already understand this recursive solution, you can skip to the next section, but if you don't completely understand this recursive part, I will be doing a small dry run in the next section for those who still didn't understand this recursive part. So let's just dry run this algorithm. We know that algorithm is not fully correct, but let's just is not fully optimal, but let's just dry run. So we want f of 0 comma 0, that is we want to partition everything starting at index 0, that is this particular array, into everything starting at index 0 here, right? So we need to partition this entire array into 3 partitions. Now what the approach is, we will just fix the first partition. So first partition should have a AND value of 0. So we'll figure out how many first partition that we can have which have an AND value of 0. So we'll see, is 3 a possible partition? Answer is no. AND value of 3 is 3, which is not 0. Is 3 comma 2 a possible partition? Answer is no. 3 comma 2, 3 and 2 is 2, which is not equals to 0. Is 3 to 5 a valid partition? Answer is yes, because 3 and 2 and 5 is 0, which is the one that we want. So one possible partition is something we found. So one of the partition could be partition it into 3 to 5, the first one, and partition the remaining element separately. So just call the same function to partition the rest of the element into rest of the partition. So f of 3 comma 1, which basically mean we have to partition everything starting at index 3. So this is the array we are looking at, and we have to partition it into everything starting at index 1, which is this part, right? So we are looking at f of 3 comma 1. Now let's look at other alternatives. So 3257 is also a valid partition. Why? Because the and of everything here is 0 as well, and in this case again what you will do is you need to partition this remaining element into these many remaining partition, that is f of 4 comma 1. So f of 4 comma 1, right? Similarly, another possible first partition could be this, right? In this case again you want to partition the remaining element into the remaining number of partition. So you want f of 5 comma 1, so f of 5 comma 1, right? And finally you have one more valid partition. In this case you want f of 6 comma 1, f of 6 comma 1, right? So these are like all the valid partitions for the first one. Now if you go here, you are looking at this particular partition, that is the value of the first array will be 5, right? Similarly, if you are looking here, you are looking at this particular partition, right? So the value would be 7. Similarly, if you are here, then you're looking at this as the first partition, so the value of this would be 7 as well, right? And finally, if you're here, you will also have value of 7, right? So why does that add 7? Because we want the sum of all partitions, and we wanted 3 partition. We are figuring out we'll get 2 partition value from here, 2 partition value from here, and so on and so forth. But the first partition is something you have to add because that's what you have just now fixed, right? So sorry. So let's move forward. Let's now figure out f of 3 comma 1, right? What does it mean? This means that we need to figure out, we need to partition everything starting at index 3, that is this particular array, right? 7 7 7 5, and we need to partition it in everything starting at index 1 here, that is in 2 partition, first with and of 7, second with and of 5. So again our approach will be exactly similar. We will simply focus on the first partition. So first partition would start at here, and we want the first partition to have a and of 7. So is this a valid partition? The answer is yes, because this has an and of 7 and we want and of 7. So if this is a valid partition, we got a sum of 7 or value of 7, and this is the remaining element we need to partition. And if you see this remaining element, we need to partition it into these all partitions. So f of 4 comma 2 is what we want, f of 4 comma 2, right? Similarly, another possible partition could be this 7 and 7, because 7 and 7 would be 7, and that is equals to what we wanted. So again, if you take this partition, you will have a sum of you will have a value of 7, and what you will want is partition this remaining array into remaining partitions, f of 5 comma 2. And similarly, this is another partition where you will have 7 7 7, and you will partition the remaining one into the last partition, right? So once we have partitioned the or once we have expanded this, let's try to expand f of 4 comma 2, right? Again, f of 4 comma 2, what does it mean? It means you have to start at index 4. So this is the array you are looking at, 7 7 5, and you need to partition it into everything starting at index 2, that is one partition with a width and of 5. So what is the valid first partition? Is this a valid first partition? The and is 7, the and we want is 5, so this is not a valid first partition. Is this a valid first partition? And of 7 and 7 is 7, but what we want is 5, so again not a valid first partition. Is this a valid first partition? And of 7 and 7 and 7 is 5, and what we want is also 5, so this is a valid first partition. So what we'll say, we have to partition this remaining element which is starting at 7, right, imaginary element, and we have to partition it into remaining partition which is starting at 3. So f of 7 3 is what we want, right? In the same fashion, if you look at, you will want f of 7 3 would be equals to 0, right? Because you are saying what is the minimum sum possible to partition no element into no partition, that is 0, right? So this will return 0, so 7 plus 0 will be 7, so this will return 7, right? And this simply will also return 0 because we already looked at f of 7 3. This will also return 0, right? So overall it will also return 7 and it will also return 7. So we are getting 7 from 3 places, so we will take minimum across all of these, right? So f of 3 1 would be 7, so 5 plus 7 is 12, so we'll get 12 from here, right? In the same fashion, if you figure out f of 5 2 is something we already calculated, and what we got f of 5 2 as okay, I think I missed 5 here, right? Because that's another partition that we have, right? So this will be 5, this will be 5, and this will be 5, right? But I hope you got the idea. This is how it will be proceeding, and finally at f of 0 0 you will have what is the minimum sum possible to partition the array starting at index 0 into all the partitions starting at index 0, right? So let's look at the pseudocode for one last time. The pseudocode was doing exactly the same thing. This was the base condition which we encountered with f of 7 3 here, right? And another base condition would be if you have already exhausted all the partitions and you still have some elements left, so in that case as well you will return infinity. Otherwise we have to do memoization here. Why? Because we already see that there are stuffs which are reappearing, so we have to save on operations, so we will simply memorize it and reuse it, right? So inside this we are simply figuring out all possible valid partitions or all possible valid first partition that will start an index, and for all of those partitions we already know the value of that. We simply partition the remaining array into the remaining partitions that we want and add them. That will be the minimum sum with that particular partition, and we will take minimum across all such valid partitions to get the final minimum value, right? So now we know that we have a order n square m algorithm that will give us the minimum sum to partition the given array into some number of partition with a given and values, right? Now we need to optimize this. First of all, which of these 3 factors you can optimize? The first n is coming from this index, second m is coming from this part, and the second n is coming from this loop, right? So if you try removing one of the indexes here, one of the parameters here of the function, that's a very I would say you have to change your complete approach itself, right? So instead let's try to see if we can optimize this for loop here, right? Now what this for loop is doing, this is iterating over some indexes, and for some of the indexes, like it skips some of the indexes first of all, and for some of the indexes it figure out f of next plus 1 part plus 1 and add the value for the current subarray, right? Now there are 2 things, it skips some part and then it does something for some part. So let's try to figure out how many does it skip. Like if we are able to skip all of these efficiently, we don't need to iterate over all the indexes to skip them, and if we just iterate over the required ones, then it may happen that it may not be order n. Instead, the valid ones might just be order log n or order root n, right? So let's first try to figure out what all we are skipping, right? So how to do that? I would strongly encourage you to pause and try to figure out which all indexes you are skipping efficiently. Okay? Now, let's say you are at this particular index I. So IND is 0. So here you will be skipping every subarray, or first of all, what you are interested in? You are interested in the first subarray that has a AND value of this, right? So you will be skipping all subarray that doesn't have an AND value of this. So is this subarray has an AND value of 1? No. Is this subarray has an AND value of 1? No. Does this subarray has an AND value of 1? Yes. So you will not be skipping this. So you will have f of next plus 1 part plus 1 for index 2, right? Similarly, let's move forward. You have skipped this, you are not skipping this. Will this have AND value of 1? Answer is yes, so you will have this. Will this have AND value of 1? Yes, you will have this. Will this have AND value of 1? No, so you will skip this. Will this have AND value of 1? Answer is no, so you will skip this as well, right? So notice what we are having is we have some indexes which we are not skipping, and then some indexes which are skipping. The interesting thing here to note is these all things are continuous, and will that always be true is the question, and the answer is yes. Why? Because what we want is we want AND value to be a particular value, right? And when you do AND from left to right, or as in when you include new elements into your array, so AND of this is some, let's say A, and AND of this would be A and 5, right? So if you include new elements in your array, the AND value would decrease. So let's say AND value is this, it will decrease with some indexes, then it will remain constant, it will again decrease, it will again remain constant for some time, it will again decrease, it will again remain constant, and that's how this function will proceed. That is, if you take AND value of everything up till here, then AND value of everything up till here, AND value of everything up till here, and you will plot this, you will get something like this, right? So just to show you this particular thing, AND value of this would be 3, AND value of 3 and 3 would be 3, AND value of 3, 3 and 5 would be 1, AND value of 3, 3, 5, 7 would be 1, 3, 3, 5, 7, 7 would be 1, 3, 3, 5, 7, 7, 6 would be 0, and 3, 3, 5, 7, 7, 6 would be 0. So notice it is decreasing first of all, and it is not strictly decreasing, rather it's constant and then decreasing and then again remain that same value, then again decrease and then again remains same. So that's how it will be, this function would be, right? Now what you want to call this function for only one particular AND value, otherwise you will skip, right? So basically what you want is you want to call the function for a range L and R only, right? So you want one specific AND value, and this AND value would occur for a range L and R. Everything before L you don't care, everything after R you don't care, right? So if you can figure out this L and R efficiently, you can avoid all the indexes before L and like after I, or for sure after between I and L you can ignore all the indexes, like you would not iterate over any of those indexes at all. And similarly between R and N you will skip all the indexes, you will not iterate over it. So this loop will simply be over L and R, given you are able to find L and R efficiently, right? Now can you find L and R? The answer is yes. The function is decreasing, so you can apply binary search. Now how to apply binary search we will discuss towards the end of the video when we will, but for now, because the function is decreasing, you can apply binary search and figure out this L and R in just log n time, right? Now again, this log n is not actually log n, we'll discuss about that, but for now, with log n operation you are able to figure out the value of L and R, and once you figure out L and R you can skip all of these things and just iterate over L and R and just do this operations, right? Now, what is the overall time complexity now? The overall complexity is again the exact same thing, number of states multiplied by what we are doing inside each of the states. So number of state is still order n into m, there's no change there. What you are doing inside each of the state, first of all, you are trying to figure out L and R. Each of these will take log n time, so 2 log n operation, overall order log n operation, and then you are iterating between L and R. So notice, even though you have reduced the iterations, but there is no fixed mathematical relations that you can establish between L and R to make sure to show that difference between L and R would be not of the order n. In fact, if you look at it, if let's say all of these were 7, just assume that, so all of these will be 1, right? So you have to iterate over all of them. So that's where like number of iteration would still be order n. It will be definitely lower than what you had previously. You are iterating from all the way up to I to n, but it will still be of the order n in worst case. So average case complexity is a lot better now, but the worst case complexity is still order n square m, right? So let's look at the pseudocode before we move forward. So pseudocode would exactly be same. Only thing that change here is we will just simply do a binary search for the starting point, and we can do binary search for the ending point as well. But here what I've done instead is I just started iterating from starting point, and ending point I will figure out on the fly. So that's another way, but it will not save anything. It just save extra logging operation, but overall it's still the same, right? Now we need to optimize this even further, right? This will not also work. So there are two possible ways now. Either you again do some observation and try to squeeze this particular operation, right? Or you convert this to bottom up and do some range query trick. Now, why I am sure that range query trick would help? Because we already know this is an operation in L to R, right? So it may happen that you can do some range query trick, and you can use some range query data such as maybe prefix sum or suffix max, suffix min, whatever you can, or maybe segment tree as well, and figure out this value min across a range efficiently. That is something you can do. So you have two choices here. Either you can go this route or you can go this route, right? We will be going both the routes in this video. First, let's go over this route, and then we will discuss the second route as well. So what we want is, we want to optimize this particular loop, right? Now there are only two ways to optimize this, or two ways to squeeze this. Either you don't have it completely, right? That's the obvious way. In this particular case, that is not possible because we are doing some operation which has some meaning to the answer, right? So you can't, either you have to prove that any of these operations would not yield better result. In other words, you have to prove that only the first subarray that I will take will be yielding the best result, others will not yield best results. Either to prove that, or if you are able to prove that, then good, like you just do this for the first element or only L, and not for everything between L and R. So that way you just skip the iteration and your complexity would reduce. In this case, that is not possible. Like you have to iterate from L to R, because that you are trying to iterate over all possible, like all possible first iterations, and it is very hard to like prove otherwise, right? Or rather it is easier to come up with a counter case that this, if you avoid all things between L and R, then you will end up having a bad answer, or rather an answer which has a value greater than what you could have, right? So second approach could be, let's remove this and defer this decision until that index arrives. What does it mean? What does it mean? It means that if here you are applying this operation on a index which occurs sometime later in the recursion. So instead of deciding what to do with that index now, we will decide when that particular index comes in the recursion. So let's look at it with an example. We are at index I, right? We want and of 1. So what we did initially is we started and take all possible valid subarray. So these are the like all possible valid subarray, all possible valid first subarray. So we took all of them, and for each of them we figured out, okay, remaining way to partition the remaining array, right? So that is what we did initially, but you can avoid taking the decision of this element and defer it until this index arrives. How? Let's say you just partition it into the first partition, like up till L, you partition this. So this is the first partition of the array. Now this particular index come. So this index, you can say either it will be a part of the new array that I'm trying to form, or new subarray I'm trying to form, or it will be a part of the previous array itself. If you do this, notice you are still covering all possible scenarios. So when you do this, you will be covering this array as well, and this array is something you had already covered. So you are still covering all possible scenario. It's just that because you are not deciding that this element will be a part of the first subarray in the iteration of 0 itself, you are deferring this decision until I equals to 3 hits, and at I equals to 3 you will decide whether to merge it with the previous one or to start a new one, right? In the same fashion, when I equals to 4 hits, you will decide whether to merge it with the previous one or start a new one. So either you will be starting a new one here, or you will be merging it with the last one, and with the last one we mean whatever was at part minus 1, right? So if you do this, you don't need this for loop here. Instead you just need a if condition here, that is whether you can what happen if you merge this, like what is the total value. Now the value of the array is something which is equals to the last element of the array, right? And because that's the case, you don't even need what is the starting point of the last index or the last part, right? So let's just take one concrete example. Let's say you are trying to partition starting at index I. You got this as the minimal partition, that is you got L here, right, for the AND stairs, right? Now you want to partition the remaining array into the remaining number of partitions, right? Now you come here, your I is this. Here you have two choices. Either you will say I will start a new partition, or you will say okay, let's merge this with the last partition. Now what is the cost of merging this with the last partition? The answer is, if you merge this with the last partition will now change to 3357, and previously you had 5 as the cost, but now the cost would be 7. So let's figure out the cost of the previous one. The cost was 5 plus f of 3 comma 1, right? Now the cost would be 7 plus f of 4 comma 1, right? Now you are standing here. F of 4 comma 1 is something that you can figure out from here, right? But how will you figure out that you need to remove 5? Like you have already taken 5, right? When you are at 3, this 5 is something you have already taken, so this 5 is there. But you are saying that it will, I want this to be a part of the last subarray itself, so I want to merge this. So I want 3357 to be a part of single subarray. So in that case, 5 is something I want to remove and 7 is the new cost of the last subarray. So what you will do, you will simply subtract 5 and add back 7, right? So this is how the pseudocode would change. Everything would remain as it is. You are just checking for the lth value or the first value. Now whenever you are entering into the index, you will now check whether is it possible to merge the current index with the last array. We already know the AND of the last array, right? We'll simply AND the current index, and if it is still equals to the AND of the last value, it means we can merge it, right? And if you want to merge it, you are extending the previous array. So previous array, the sum was 5, right? And from the previous array, what you have called is f of 3 comma 1. That is, you want what is the minimum sum that you can get to partition everything starting at 3 into every partition starting at 1, right? So you only want the value of these partitions starting at 1, but now you are saying that okay, this index 3 is not a part of the current subarray, instead it is a part of the previous subarray. So whatever value you get, let's say you get x from here, so you will simply subtract 5 from there and add 7, and this will give you the remaining delta that you would have added if you have taken 7 as the first subarray itself, right? So that's the only thing that changed here. I know that is a bit tricky, so I would encourage you to pause and try to do a dry run. I'm not doing dry run because that will make the video a bit longer. So overall, we are deferring the decision of what to do with the current index to the time when that index hits, and that's a very standard technique. And to actually come up with this kind of observations, you need to actually practice a lot. So this may in real context, you may or may not be able to come up with this kind of observations at that very instant, right? So overall, if you have this, the complexity is now order n into m itself, n into m into log n, right? Because you are still finding out this L with the binary search. So the complexity is just order n into m into log n. And let's look at how to implement this. This function is straightforward. We have already looked at the dry run of this. Only thing that we haven't looked at yet is this binary search part. So let's look at this binary search part, look at the implementation of this, and then we will trace back and see how to convert this to bottom up and then do some range query tricks to solve the same. Okay. So we have to do binary search, that is starting at index I, we need to tell what is the first index where the AND is a particular value x, right? So let's say the x we are looking for is 1, right? So we want to figure out, starting at index I, what is the first index where the AND would be 1, and similarly what is the last index where the AND would be 1. So last index you don't want right now, but we'll need that when we discuss the bottom up solution. So here, as we already discussed, the AND function would look something like this, a staircase, right? Now we want these two indexes L and R, so we need to binary search for that. So our L or binary search leftmost part is this, binary search rightmost part is this, right? And we are looking for this particular value and this particular value, right? So first of all, this value, the first index where the AND is 1, right? So what we'll do, we will simply take a mid of L and R. So mid of L and R would be 1 plus 6 by 2, which is 3, around 3. So you will land here. You will check whether it is equals to 1 or not. If it is not equals to 1, sorry, if it is greater than 1, then you will search in the right half. if it is less than equals to 1, you will search in the left half, right? So in this case it is less than equals to 1, so you will search in this particular half. So you will simply make your R as this, right? And you will now search in this range. So L and R, M would be this again. M is less than equals to 1, so you will simply search in this half. L and R, M would be this. M is now greater than equals to 1, so greater than 1, so you will simply shift your value. Now L and R are equal, so this is your index, right? That's how you will do binary search. Now this is something which is easy if you have this array with you, this AND array with you, right? But you will not have AND array, because building this AND array would require order n square time, because to build this AND array, for every index you need to start a fresh array. Like for index starting at here, AND would be different. Similarly, if you start AND array from here, the value would be different, right? So you can't have this AND array, and that's why the binary search that we looked at is that simple. It's not that simple. So let's say you are again at M here, so you want this one, that is you want what is the AND of this range, everything starting at I up till M, right? So how you will get this? You can use any range query data structure. Either you can use segment tree here, that will give you AND of a range efficiently. So overall your binary search will take order log square n time, right? Because you will be doing log n, you will be checking log n indexes, and for each log n indexes you will be finding out the AND. So there are total log n number of M you will check, and for each M you will need to figure out the AND of everything between I and M. That will take you log n time. So overall complexity would be order log square n. Now again, that is something if you use binary search, segment tree to figure out the AND. Now another easy way to find out AND would be if you maintain a simple bitwise representation of every number. So 3 is mapped as this, right? So this is 0, this is 2 power 1, 2 power 2, 2 power 3, right? So 3 is written as 1100. Similarly, 9 is written as this, and so on and so forth. Now let's say you want to figure out what is the AND of everything between this I and this M, right? You want AND of these three numbers 1, 2 and 3. So what is actually AND? And let's figure out the bitwise AND of every bit one by one. So the AND would be 1 here only when all the bits are 1 in between, right? So what you can do, you can maintain a prefix sum for each bit, and once you have prefix sum, you can figure out how many bits are set here, and if number of bits set is equals to number of elements here, you know that this bit will be set in the bitwise AND. Otherwise this bit will not be set, right? So similarly, you will figure out how many ones are there. You will say only 1, but there are 3 elements here, so this bit will not be set. Similarly, you will see there are 3 numbers but only 2 ones, so this bit will not be set. Similarly, there are 3 numbers but only 1 bit is set, so this bit will not be set. So overall the bitwise AND would simply be 1, right? And that is what we have. So this way you can do a bitwise operations. So what you are doing for each I to M, figuring out the bitwise AND, you are iterating over all the bits, and iterating over all the bits will take you order of bits time, and order of bits will also be of the order of log of V, where V is the value, right? In the given problem, value was also up to 10 power 5, so you can assume log of V as log of n itself. So complexity of either use binary search using segment tree and binary search using this prefix sum, both will take order log square n time, right? So the complete complexity would be order nm multiplied by log square n, right? And which will pass the given time constraint, right? So next, looking at the code, but if you have watched this point, I would strongly encourage you to pause and try to code this entire thing by yourself. Let's look at the code now. First, let's look at the brute force one, which we have seen. So we will simply try and figure out the bitwise AND for everything between I and n. So that we know that it will not pass. You can just uncomment it and go and submit it. It will fail at some test cases, right, with time limit exceeded. Now this is the next part where what we are doing is we are figuring out the value of 1 comma 1 and inside this what we are doing is we are checking whether the current element can be a part of previous partition or not. If it can be, I will try make it a part of previous partition. So the new partition would now start at index plus 1 or may start at index plus 1, and because the current element is a part of previous partition, we will add the differences that incur because of this in the previous partition itself, right? So just to reiterate that part, previous partition, so let's see this one. Yeah, so previous partition in this particular case was ending at 5 previously, right? So we called f of 3 comma 1 with a 5 added here, right? But if the previous partition ended at 7, what we would have called? We would have called 7 plus f of 4 comma 1, right? Now you are at index 3. At index 3, you said okay, 3 is a part of previous partition. So you still call f of 4 comma 1. That is fine. F of 4 comma 1 is something you are getting added. But notice previously 5 was the cost of the first partition, but now the cost is 7. So you need to somehow add back 2. And how you will add that? You know that because 5 was the last element and last element is the value here. So you will simply subtract 5 and add back the current cost, which will be 7. So overall you will be adding 2 more, which will make up for the 7, right? So either you will do this, or the second approach would be you start a new partition here, and you can do this only when the part is less than equal to total parts. So in this case, again, you will first figure out the leftmost value or the L. Now this part you can do using binary search. I ended up writing a single for loop here, like kind of linear search, and it passed the given time constraint, which it should not have ideally, but I think the test cases are weak, so it passed it. But ideally this should have been replaced with a binary search that we have just discussed in this part, right? So once you figure out this next value, you can simply do min value of next plus 1 comma part plus 1 and then array of parts, right? So hope this solution is clear. Now comes the next part, that is we figured out that we have to do something for L and R, but we don't want, like, we don't somehow made or able to make this observation, right? Let's say I was doing the contest and I was not able to make this observation somehow, right? Though I would say that these kind of observations you should try, because this is pretty standard trick that what you are trying right now, you can defer it until that index. So we have done different questions as well using this trick in the past. So just try to apply this trick, but again, during the contest it may happen you will not be able to get it. It happens with the best of us. So in that case, what I would have tried is what I'm trying to explain here. Again, it might not be something that will yield the best result, but at least when I am in the contest, I would go ahead with that approach and still try to like think in that direction, right? So the direction is convert the solution to bottom up and then see if this L comma R can be optimized a bit, right? So let's look at that. So we, first of all, conversion from top down to bottom up is very straightforward. We have discussed this multiple times in this channel. What is the trick? Trick is whatever you have in the top down, you will copy the exact same thing except the base case. So in this case, the base case is np as 0, and also like n of everything else as infinity as well. I forgot that. So these are the two base cases that we have. Now once you had this base case sorted out, you can simply iterate over all the index and the parts, and after that you can just copy paste what you had inside the inside each of the state calculation for top down approach, right? This is exact copy paste. I've not done anything else except I've changed this, replaced this answer with dp of index comma part, right? That's the only thing I have changed here. Now at this stage, you know that this is something you can figure out using, like this is something you can figure out using binary search. And at this stage you also know that you don't need to iterate over all of this. Instead you can also figure out the right half as well, like the right part until which it will go, right? So your main goal is between a range, what you are looking at is you are looking at array of next plus dp of next plus 1 comma part plus 1, right? In other words, part plus 1 is kind of constant here because part plus 1 is fixed. You are looking at for a particular part for next few indexes. So let's say this is a array you have, right? This is a dp array you have, right? And this is a 2D dp array because you will have parts as well. So let's assume there are 3 parts or 3 partitions you need to partition the entire thing into. So you have three things with each indexes, right? So at 0 you will have part 0, part 1, part 2, at 1 part 0, part 1, part 2, and so on and so forth, right? So this is how your dp array would look like. Now let's see what you are doing for I and p, right? So you are filling up this particular value. So for this particular value, let's say you know that this is L and this is R, assume that, right? So for this particular value, what you're doing is you are looking at L and part plus 1 and then array of L plus 1 part plus 1 array of L plus 1, L plus 2 part plus 1 array of L plus 2, and so on and so forth, R part plus 1 array of R. So in other words, you are looking at part plus 1 always. So that is you are looking at this particular piece, and among this piece also you are looking at these two things, and among these two things you know array of next value already, so you can simply add them up here and you can simply take a range maximum across these. And for range maximum you can use segmentary or fragmentary or whatever your choice, whatever is your choice, right? Again, my motive with this was not to make the problem complex or overkill with segmentaries here, but this is like the usual way where you will think in case you are not able to optimize top down further. So what we have done, we have completed the bottom up, and we saw that it's a range, it's doing something in the range. So whenever we figure out the value of a particular index, we will simply update that particular segment tree. So let's say you maintain 3 segment tree here, one for this, one for this, one for this. Whenever you find the value, you update the particular value in the segment tree. Now you already have segment tree built with all these things, right? So what you just need is you just need to query a range L to R in this segment tree, and that's it, right? So if you have followed through this point, and if you have watched at least the first video of segment tree in this in the segment tree series of this channel, I would strongly encourage you to code this solution by yourself, because even though it might feel overkill, but if you code this entire thing by yourself, you will be able to retain this piece or this optimization from a long time, and it might help you in future contests as well. So with that, we'll end the video here. I'm not showing the code for this because that might feel overkill to most of you. So, but if any of you interested, I am more than happy to share it in the description or review any of the code that some of you my guys might write after this. So that's it for the video. If you have any doubts, feel free to post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. I will see you in the next one. Thank you.